For millennia, humans have gazed up at the night sky, our eyes drawn to the luminous orb that hangs there, the moon. It has been our companion, our muse, and the source of countless myths and legends. But have you ever wondered where the moon came from? Today we unravel the mysteries behind our celestial neighbor, exploring the top theories about its birth and evolution. From colossal collisions to celestial captures, we'll journey through time and space, examining the scientific evidence and weighing the plausibility of each theory. Prepare to delve into the heart of a cosmic puzzle that has captivated astronomers and dreamers alike for centuries. Imagine, if you will, the early solar system, a chaotic ballet of newly formed planets and planetesimals, their orbits still settling into a familiar rhythm. In this cosmic dance floor, collisions were not uncommon, and perhaps one such collision, more dramatic than any other, gave birth to our moon. This is the crux of the giant impact hypothesis, a theory that has become the leading contender in our quest to understand the moon's origins. This hypothesis proposes that a Mars-sized object, which astronomers have dubbed Theia, slammed into the young Earth billions of years ago. The impact would have been cataclysmic, an event of unimaginable energy, melting and vaporizing vast portions of both bodies. Debris, flung outwards in a superheated cloud of molten rock and vaporized minerals, would have circled the Earth in a ring of cosmic destruction. Over time, this debris, bound by gravity's invisible hand, would have coalesced, clumping together into larger and larger bodies, eventually forming the moon we know today. Evidence for this theory lies in the moon's composition, which bears striking similarities to Earth's mantle. Additionally, the relatively low density of the moon suggests it formed from the outer layers of the Earth and the impactor, rather than their denser cores. But like any good cosmic mystery, questions remain. Why is the moon so large compared to other moons in the solar system? Why does its orbit lie on a different plane than Earth's equator? These are puzzles scientists are still piecing together, searching for further clues to confirm or refute this dramatic origin story. Could our very own Earth, in its infancy, have spun off a piece of itself, a celestial offspring, that would become our constant companion in the vastness of space? This is the intriguing proposition of the Fission Theory, a hypothesis that suggests the moon was once a part of Earth. Picture this, the early Earth, still a molten ball of rock and metal, spinning at a dizzying pace, much faster than it does today. Centrifugal force, pushing outwards from the axis of rotation, could have, according to this theory, ripped a chunk of the Earth's mantle away, flinging it into orbit. This ejected material, still bound by gravity, would have cooled and coalesced, forming the moon we see today. The Pacific Ocean basin, with its vast emptiness, was once proposed as a scar left behind by this dramatic event. While intriguing, the fission theory struggles to explain several key observations. The angular momentum of the Earth-Moon system, for instance, would have been much higher if the Earth had once spun fast enough to fling off a piece of itself. Additionally, the compositional differences between the Earth's crust and the Moon's surface raise further doubts about this theory's validity. While the fission theory may not be the most likely explanation for the Moon's existence, it serves as a reminder that our understanding of the cosmos is constantly evolving, and even the most seemingly solid theories can be challenged by new discoveries and perspectives. Chapter 3. The Capture Theory, a celestial wanderer ensnared. Imagine a lone traveler, a celestial nomad wandering the vast expanse of the early solar system, its path shaped by the gravitational pull of larger bodies. This wanderer, a protoplanet forged in the same nebula that birthed our sun, stumbles upon the Earth, its journey forever altered by this cosmic encounter. This is the essence of the capture theory, a hypothesis that proposes the moon formed independently of Earth, only to be ensnared by our planet's gravitational pull during a close encounter. Captured into orbit, this celestial wanderer became our constant companion, its destiny forever intertwined with our own. This theory finds some support in the diversity of objects found within the asteroid belt and the Kuiper belt, suggesting that protoplanets could have formed in various regions of the early solar system. The capture of a wandering moon could also explain the unique orbital characteristics of some moons in our solar system, such as Triton, Neptune's retrograde orbiting moon. However, capturing a moon-sized object requires a delicate gravitational dance, a series of unlikely events that would slow down the incoming body enough for it to be captured into a stable orbit. Additionally, the compositional similarities between the Earth and Moon present a significant challenge to the capture theory. While the capture theory may not hold all the answers, it highlights the dynamic and ever-changing nature of the early solar system, a period of intense planetary migration and gravitational interactions that shaped the celestial tapestry we observe today. Chapter 4. The Co-Formation Theory, Partners in Planetary Formation. In the swirling disk of gas and dust that birthed our sun, countless particles collided, clumped together and grew, their fates dictated by gravity and the delicate balance of forces at play. What if amidst this cosmic ballet, the Earth and Moon formed side by side, partners in planetary formation from the very beginning? This is the premise of the co-formation theory, a hypothesis that suggests the Earth and Moon coalesced from the same region of the protoplanetary disk, their destinies intertwined from the earliest moments of their existence. This theory draws parallels with the formation of binary star systems, where two stars are born from the same collapsing cloud of gas and dust. Similarly, the co-formation theory proposes that the Earth and Moon grew together, their gravitational pull attracting and accumulating material from their surrounding region of the protoplanetary disk. However, the co-formation theory struggles to explain the significant differences in density and composition between the Earth and Moon. If both bodies formed from the same region of the protoplanetary disk, one would expect their compositions to be more similar than what we observe today. While the co-formation theory may not provide a complete explanation for the Moon's origins, it reminds us that the formation of planetary systems is a complex and often messy process, with multiple mechanisms potentially contributing to the diversity of celestial objects we observe today. Chapter 5. The Synestia Theory, a molten donut and the birth of a moon. Imagine a scene of unimaginable violence and beauty, where a young, molten Earth, still reeling from a colossal impact, finds itself enveloped in a superheated cloud of vaporized rock and metal. This cloud, spinning rapidly, forms a bizarre, donut-shaped structure called a synestia, a short-lived but crucial stage in the evolution of both the Earth and Moon. The Synestia Theory, a relatively new addition to the menagerie of lunar origin hypotheses, proposes that the Moon formed within the outer layers of this spinning, vaporized Earth. As the synestia cooled and contracted, material within this cloud condensed, eventually coalescing into our familiar lunar companion. This theory elegantly explains some of the Moon's unique characteristics, such as its isotopic similarities to Earth and its slightly different chemical composition. The Synestia theory suggests that the Moon formed from the outer layers of the synestia, which would have been enriched in certain elements compared to the Earth's core. While still in its early stages, the Synestia theory has the potential to revolutionize our understanding of how the Earth and Moon formed. It offers a compelling explanation for some of the long-standing mysteries surrounding our celestial companion and opens up new avenues of research into the chaotic early days of our solar system. As we delve deeper into the cosmos, armed with ever more sophisticated tools and a thirst for knowledge, we continue to refine our understanding of the universe and our place within it. The quest to unravel the Moon's origins is just one piece of this grand cosmic puzzle, a journey of discovery that inspires us to look up in wonder and contemplate the vastness of the universe and the mysteries it holds. The Moon's enduring enigma. From giant impacts to celestial captures and spinning clouds of vaporized rock, we've explored the leading theories about the Moon's formation, each offering a unique perspective on this enduring cosmic mystery. While the debate continues, one thing remains certain: the Moon's story is inextricably linked to our own. As we continue to explore our celestial neighbor both robotically and with human footsteps, we unlock further secrets about its past and gain a deeper appreciation for its profound influence on our planet and our lives. The Moon's phases mark the passage of time, its gravity governs the tides, and its gentle light has inspired poets, artists, and dreamers for millennia. What do you think is the most plausible theory? Let us know in the comments below. And stay tuned for more cosmic mysteries, and don't forget to like, share, and subscribe for more fascinating content.